Hello students, today we shall discuss about the crystallography, physical chemistry part crystallography we shall discuss in detail. Crystallography is a branch of physical chemistry which deals with the structure and arrangements in a crystal. Now actually crystallography is the solid state. Matter is existed in three physical states: gaseous state, liquid state and solid state. Now this gaseous state on cooling is converted into liquid state. Liquid state on cooling it is converted into solid state. At ordinary conditions, some material, some matter is existed in gaseous state, hydrogen, oxygen, nitrogen, etc. Some of the matter is existed in liquid state, water, organic liquids, so many substances, and many of them they are existed in solid state. On the conversion of liquid state to solid state, these molecules or atoms, they are arranged. This arrangement is of two types. One is systematic arrangement of atoms or molecules in a solid. Another way is irregular arrangement of the solid. So depending upon their arrangement of atoms or molecules in a solid can be classified into two types. One is amorphous solid and crystalline solid. Now let us see the difference between amorphous solid and crystalline solid. In an amorphous solid, the atoms or molecules, they are not regularly arranged. There is irregular arrangement of atoms or molecules in an amorphous solid, whereas in a crystalline solid there is a regular arrangement, systematic arrangement of atoms or molecule in the solid state. See, systematically arranged in case of crystalline solid. So orderly arrangement, disorderly arranged, disorder and order. So first difference between a solid, amorphous solid and a crystalline solid is that in an amorphous solid, arrangement is not regular, disorder arrangement of atoms or molecules, and there is orderly arrangement. There is orderly arrangement of atoms or molecules. That is the first difference. So examples for these two types, amorphous solids and crystalline solids, you can take examples: rubber, polymers, plastics. So many examples are there for these amorphous solids, whereas examples for crystalline solids, you can take sodium chloride, barium chloride, ionic crystals, then you have iron, copper, metallic crystals, and you have ice, molecular crystals. These are all the examples of crystalline state. Amorphous state, rubber, polymers, plastic, so many things are there. So like this we can have two types of solids and examples. Now we have considered their arrangement and examples, different types of crystals. These crystalline state, these crystals are anisotropic in nature, whereas these are isotropic. What is meant by isotropic and anisotropic? Isotropic means similar. Anisotropic means there is a difference. What is that difference? Let us see. Physical properties at different angles, different directions are different. That is anisotropic. Whereas the properties, physical properties and many properties, they are same in any direction or in any angle, they are the same. That is isotropic. Amorphous solids are isotropic and crystalline solids are anisotropic. For example, reflection of light. Reflection. When light falls on a crystal, the reflection is different at different directions, physical property. Whereas there is no reflection at all, no reflection, even though if there is reflection in some of the substances, the reflection will not change in any direction. So, the change in the direction, anisotropic, there is no change, that is isotropic. Therefore, amorphous solids are isotropic in nature, whereas crystalline solids are anisotropic in nature. Now, regarding the melting point, when you heat a solid substance, there is no sharp melting point. There is no sharp melting point. A range of melting point is there in case of an amorphous solid. There is no sharp melting point. A range of temperature is there, melting point. Whereas in case of crystalline solid, there is a sharp melting point. There is a sharp melting point. There is a range of melting point. There is a range of melting point in case of amorphous solids. Sharp melting point in case of crystalline solids. Another difference is that there is symmetry elements here. So, symmetry elements, I will explain that symmetry elements later. Symmetry elements are there in case of crystalline solids. There is no symmetry elements. No symmetry elements. No symmetry elements. That is the difference. So, these are symmetry elements are there. There are no, I will explain these symmetry elements later. Symmetry elements are there in crystalline, any crystalline solid, whereas there is no elements of symmetry here. Now, another difference is heat of fusion. Heat of fusion. Heat of fusion. Heat of fusion. In case of heat of fusion, there is a definite value of delta H fusion in case of crystalline state. Delta H fusion, there is an accurate, there is an exact delta H fusion. When it is fused, fusion takes place and there is a particular specific delta H fusion in case of crystalline solid, and in case of amorphous solid, there is no definite heat of fusion here. Like this, there are so many differences between amorphous solids and the crystalline solids there. Now, let us explain about the elements of symmetry in a crystalline solid. In a crystalline solid, systematic arrangement is there, atoms and molecules, and as I told you, there is symmetry element in a crystalline solid. What is an element of symmetry? How many types of elements of symmetry are there in a crystal? Actually, there are three types of elements of symmetry in a geometrical shape. One is axis of symmetry. Axis of symmetry. Another one is plane of symmetry. Plane of symmetry. And third one is center of symmetry. Center of symmetry. Center of symmetry. Axis of symmetry. Plane of symmetry. And center of symmetry. Any geometrical shape has a specific number of these elements of symmetry. Elements of symmetry can be defined as it is the element of symmetry which gives two or more identical shapes on rotation. That is the symmetry element. Now, let us go in detail into the axis of symmetry. Axis of symmetry is an imaginary line passing through the crystal. When it is rotated through 360 degree rotation, the similar appearance is repeated more than once. That is called axis of symmetry. For example, if you take a rectangle, you pass an imaginary line through this rectangle, you rotate this, the appearance will be repeated twice. This is called C2 axis of symmetry. Now, when a geometrical shape is rotated through an imaginary line, the same appearance is repeated more than once, then only it is called an axis of symmetry. In case of a rectangle, the same appearance is repeated twice, hence it is C2 axis of symmetry. But now you see, this is the rectangular shape, Now you consider an imaginary line passing through this rectangle. Now you see this face, this is length and this is breadth. Now this length shape is repeated twice on rotation through 360-degree angle. Second time, and original side comes here. So therefore, this is C2 axis of symmetry. In a rectangle, the same appearance is repeated twice on rotation through 360 degree. That's called C2 axis of symmetry. A rectangle has a C2 axis of symmetry. Suppose if the same appearance is repeated thrice, such an example is, you take an equilateral triangle, you consider an imaginary line passing through, you rotate this to 360 degree. Now, if you rotate this equilateral triangle through this imaginary line through 360 degree rotation, the appearance will be repeated 3 times. Therefore, this has got C3 axis of symmetry. So, an equilateral triangle has got C3 axis of symmetry. Now, this is the equilateral triangle, this is the face 1, If you rotate this through 360 degree, see the appearance, how many times it is repeated. Now, you see this is the second appearance on rotation. Next, if you rotate this, you will get third appearance. If you continue the rotation, it will be repeated. Therefore, a triangle, an equilateral triangle, on rotation through 360 degree, the same appearance is repeated thrice. That's why it is called C3 axis of symmetry. So, in case of equilateral triangle, it has got C3 axis of symmetry. Similarly, come to a square. You consider an imaginary line passing through this, you rotate this to 360 degree. Now, how many times the same look, the same appearance is repeated on rotation of a square? The same appearance will be repeated 4 times. I will show this shape here. Now, you consider a square. Now, you see, you consider the imaginary line passing through this square. You rotate this square through 360 degree. This is the first appearance, first face. Now, you rotate this, you will second face, same type of face appears here. Now, you rotate, continue the rotation, third time, and this is the fourth time, and it will be repeated. Therefore, on rotating a square through 360 degree, the same appearance will be appeared 4 times. Therefore, a square has got C4 axis of symmetry. In case of a square. Now, in case of a pentagon, what happens? In case of a pentagon, you consider an imaginary line passing through this pentagon. Now, this is the first appearance. Now, when you rotate this, what happens? Similar appearance will not reappear here. Now, you consider this edge is towards left here. Now, if you rotate this, second face will come here, but this edge will be more than the earlier one, more than the earlier. Therefore, no similar appearance. Now, if you rotate this third, now what happens to this? This edge, opposite side edge, goes towards left. Earlier it was towards this side, now it is towards that side. There is no similar appearance. Similarly, fourth face here, in the fourth face, again this edge is towards this side. No similar appearance. Therefore, on rotation of a pentagon through an imaginary line through 360 degree, the same appearance will not at all repeated. No repetition of the appearance. Therefore, there is no axis of symmetry in case of a pentagon. No axis of symmetry. Therefore, in case of pentagon, it is not a symmetric one. It is not symmetric one. Therefore, no axis of symmetry in case of a pentagon. Similarly, if you take a hexagon, now you see here, this is the first appearance, first one, second one, third one, fourth one, fifth one, sixth one. 6 times it will be reappeared. So, in case of a hexagon, if you see the shape when rotated through 360 degree, 6 times it will be reappeared. Therefore, it has got C6 axis of symmetry, 6-fold axis of symmetry. So, rectangle C2, 2-fold axis of symmetry, triangle 3-fold axis of symmetry, square C4 a 4-fold axis, C4 axis of symmetry, pentagon no axis of symmetry. In case of a hexagon, C6 axis of symmetry, 6 times it is repeated. Therefore, 6-fold axis of symmetry is there. So, these are the axis of symmetry, elements axis of symmetry. Symmetry elements when observed when rotated through 360 degree. So, this is about axis of symmetry. So, now if we know this axis of symmetry, we can apply that to our crystals. How many axes of symmetries are there in a crystal that we can study a crystal, and how many axes of symmetry are there, we can easily study. Now, come to the plane of symmetry. What is a plane of symmetry? A plane of symmetry is an imaginary two-dimensional plane, passing through the crystal. Half of the image will be exact mirror image of the remaining half. That is called a plane of symmetry. A plane of symmetry is a two-dimensional plane passing through the crystal. Half of the crystal is the exact mirror image of the remaining half. Two are mirror images of, two parts are mirror images of each other. That is called a plane of symmetry. So, a plane of symmetry is a two-dimensional plane passing through a crystal. One half of that is the exact mirror image of the other half. That is called a plane of symmetry. Now, how many types of plane of symmetry? There are different types of axis of symmetry, whereas in case of plane of symmetry, there are only 2 types of planes of symmetry. So, now let us observe how many planes of symmetry in a geometrical shape. Plane of symmetry. So, plane of symmetry is an imaginary plane, two-dimensional plane passing through the crystal, half of which is the exact mirror image of the other half. That is the definition of plane of symmetry. So, a plane of symmetry is an imaginary two-dimensional plane passing through the crystal. Half of the crystal is the exact mirror image of the remaining half. That is called a plane of symmetry. How many types of planes of symmetry are there? There are 2 types of plane of symmetry. One is called diagonal plane of symmetry. Another one is called horizontal plane of symmetry. And another one is diagonal plane of symmetry. Horizontal is also called rectangular plane of symmetry. So, rectangular plane of symmetry, this is one type. Another type is diagonal plane of symmetry. So, rectangular plane of symmetry and diagonal plane of symmetry. Now, let us see what is this rectangular plane of symmetry and diagonal plane of symmetry by considering a cube. In a cube, what happens in a cube? Now, if you pass a plane of symmetry through this cube, plane of symmetry, left half is the exact mirror image of the right half. Left half is the exact mirror image of the right half. So, this is called rectangular plane of symmetry. So, it can be represented like this. You consider a cubic structure. Now, I will represent here this rectangular plane of symmetry. Now, you see here. See this. Middle one, a plane of symmetry which bisects the cube into two parts. Right part is the exact mirror image of the left part. So, this is the rectangular plane of symmetry or vertical plane of symmetry. So, rectangular plane of symmetry bisects and it is passed through the faces, one of the faces like this. Either you pass that plane here or here, anyway. This plane of symmetry bisects this cube into two equal halves. One half is the exact mirror image of the other and it is represented like this. What is diagonal plane of symmetry? In case of diagonal plane of symmetry, if you take a cubic structure, now you pass that plane through the edges. See, through the edges. So, this is the edge and this another edge. You pass that plane through the opposite edge. Now, this bisects this cube into two equal halves. One half is the exact mirror image of the other half. So, this plane of symmetry is called diagonal plane of symmetry. So, therefore, rectangular plane of symmetry is there and the diagonal plane of symmetry is there in any crystal. Some crystals they have diagonal plane of symmetry, some crystals they have rectangular plane of symmetry, some of them have axis of symmetry and so on. So, last one is center of symmetry. What is center of symmetry? There can be only one center of symmetry in any geometrical shape. For example, if you take a circle, it has got a center of symmetry. How to define a center of symmetry? A center of symmetry is a point at the center of the crystal which meet the opposite faces at equal distance. Now, consider a cube. From the center of the cube, if you draw a line to the exactly opposite edges, it meets the border, it meets the edge at the same distance. That is the center of symmetry, and there can be only one center of symmetry. A center of symmetry in a crystal is the center of the crystal which meets the opposite edges, opposite borders at the same distance. So, the distance is same. So, that is called the center of symmetry, and there can be only one center of symmetry. So, therefore, only three types of symmetry elements are there in any crystal: axis of symmetry, plane of symmetry and center of symmetry, and there can be only one center of symmetry which meets the opposite borders at the same distance, that is the center of symmetry. There are several axes of symmetry as I told you earlier, and two types of planes of symmetry and only one center of symmetry. This is about symmetry elements in a crystal. Now, let us apply this symmetry element concept to symmetry elements in a cubic crystal. How many elements of symmetry are there in a cubic crystal. Let us study that in detail. Okay. Now, we know about different elements of symmetry, axis of symmetry, plane of symmetry and center of symmetry. Now, let us apply this concept to a cubic crystal. How many elements of symmetry are there in a cubic crystal? Let us see that. Now, in a cubic crystal, different elements of symmetry are possible. Now, you see these are the faces of a cube. How many faces are there? 6 faces are there. 1, 2, 3, 4, 5 and 6. There are 6 phases in this cubic crystal. Now, consider imaginary line passing through the opposite faces. So, if you rotate this face through 360 degree, it will be repeated 4 times. That is why it is called C4 axis of symmetry. So, an imaginary line passing through the opposite faces gives C4 axis of symmetry. How many C4 axis of symmetry are possible here? Since there are 6 phases, for each axis passing through the opposite faces, 3 axes are possible, which gives the same appearance 4 times, or C4 axis of symmetry. So, therefore, total number of axis of symmetry 4-fold, that is C4 axis of symmetry, 4 numbers, 3 numbers. Since there are 6 faces, 3 C4 axis of symmetry. So, on rotation, the same appearance repeated 4 times. That is why it is called C4 axis of symmetry, and 3 numbers are there. Now, consider another axis of symmetry. 6 faces are there. Now, you see the number of edges 1, 2, 3, 4, 5, 6, 7, 8. There are 8 edges in this cube. There are 8 edges. You consider an imaginary line passing through the opposite edges. Now, when you rotate this crystal about this axis passing through the edges, how many times the same look, the same appearance is repeated? You consider this edge is towards you, 1, you see, 2, 3. 3 times it is repeated, you see. See this black, for example, this is the black edge, 1, red edge, 2, blue edge, 3, black edge is repeated. So, 3 times the same look, the same appearance is repeated on rotating this crystal through the opposite edges, 3 times it is repeated. That is why it is called C3 axis of symmetry. Therefore, C3 axis of symmetry, by passing through the opposite edges 3 times it is repeated. That is why it is called C4. This is C4 axis, this is C3 axis. How many C3 axis? How many numbers are there C3 axis? For that, how many edges are there? There are 8 edges. See, this face 4 edge, opposite face 4 edge. There are totally 8 edges. Therefore, 4 axes are possible, 3-fold. So, 4 axes, C3 axis, 3 times it is repeated, 4 numbers. There are 4 numbers. There are 4 C3 axis of symmetry passing through the opposite edges. There are 8 edges, therefore 4 axes, 4 axes of 3-fold axis of symmetry. So, that is over. Next come to these edges. I told you earlier corners, these are edges. There are 8 corners and these are edges. How many edges are there? There are 8 corners, C3 axis, and you see these opposite edges. How many edges are there? Now, in this face, 4 edges, opposite face 4 edges, and here 4 edges. There are totally 12 edges. 12 edges. So earlier we have counted not edges, corners. Corners. Now come to edges. Okay. Edges. Now you see blue, black, yellow, red. 4 edge. Here 4 edge and here 4 edge. Totally 12 edges. 12 edges. Now you consider an imaginary line. Consider imaginary line passing through opposite edges like this. Opposite edges. You rotate this through 360 degree. How many times? The same appearance will be repeated. Now you see this edge is towards you. This edge is towards you. Now you rotate this through 360 degree for the same look. This edge come to your side. This edge brown. This edge comes to your side. The same appearance repeated only twice, 2 times. When you rotate this crystal about the line passing through the opposite edges, only 2 times the same appearance will be repeated. You see, this one time, and this is second time. Only 2 times. Therefore, this C2 axis of symmetry. An imaginary line passing through the opposite edges. C2 fold axis of symmetry. There are 12 edges. Therefore, 6 number 6 C2 fold axis of symmetry are possible. So, C2 axis of symmetry 2 times it is repeated. C2. There are 12 edges. Therefore, 6 numbers. 6 numbers. Totally 6 plus 2, 6 plus 4, 10, 13. So, there are 13 axes of symmetry possible in case of a cubic crystal. 13 axes of symmetry are possible in case of a cubic crystal. C4, 4-fold axis of symmetry, 3 numbers passing through the opposite faces. C3, 3-fold axis of symmetry, 4 numbers passing through the opposite corners. C2, 2-fold axis of symmetry passing through the opposite edges, 6 numbers, totally 13 axes of symmetry are possible in case of a cubic crystal. Now come to the plane of symmetry. How many planes of symmetries are there? Plane of symmetry. Plane of symmetry. What is a plane of symmetry? It is an imaginary 2-dimensional plane passing through the crystal. One half of the crystal is the exact mirror image of the other half. That is the definition. One half of the crystal is the exact mirror image of the other half. Now, let us pass a plane through this crystal. Through this crystal. A plane is a 2-dimensional plane passing through the crystal. Now, if you pass this plane through this crystal, you will get 2 images. One is the exact mirror image of the other. So, this is the plane. What is the plane? This one is rectangular plane. Rectangular plane passing through the opposite faces. Opposite faces. This is one plane. Rectangular plane. There are 6 faces. Therefore, 3 rectangular planes passing through the opposite faces are possible. Rectangular planes. So, rectangular planes passing through the opposite faces. 6 faces. Therefore, this is 3 numbers. 3 rectangular planes are possible in a cubic crystal passing through the opposite faces. One plane, second plane and third plane. 3 planes. Another rectangle. Now come to diagonal plane. Diagonal plane. Diagonal plane passing through the opposite edges. Passing through the opposite edges. A plane, 2-dimensional plane. 2-dimensional cannot pass through the corner. Only edges. So, 2 edges, if you pass an imaginary line through these 2 edges, you will get 2 mirror images. 2 mirror images. Therefore, a plane is one which passes through the opposite edges. How many edges are there? There are 12 edges. 4 edges this face, 4 edges opposite face and 4 edges in between. Totally 12 edges. Therefore, 6 diagonal plane of symmetries are possible here. which gives 2 mirror images. So, 12 edges, 6 diagonal plane of symmetry. A cubic crystal has got 6 diagonal plane of symmetry and 3 rectangular plane of symmetry. Rectangular plane passing through the opposite faces, diagonal plane passing through the opposite edges. Therefore, total number of symmetry elements, plane of symmetry, totally 9 numbers. 9 numbers. There are 9 planes of symmetry and 13 axes of symmetry. Okay. Now come to the third type of symmetry element, that is the center of symmetry. Center of symmetry. So, how many center of symmetries are there in case of a cubic crystal? A center of symmetry is a point at the center of the crystal which meets the opposite border at the same distance. Now, if you consider the center of this cube, you go to the opposite border, you will meet at the same distance, opposite way, whatever may be the border, you will meet at the same distance. Therefore, any crystal can have only one center of symmetry. Therefore, even in the cube, there is only one center of symmetry. There is only one center of symmetry. There is only one center of symmetry. Total number is 23. There are 23 elements in a cubic crystal. 13 axis of symmetry, 9 plane of symmetry and 1 center of symmetry. So, total number is 23 elements of symmetry are there in a cubic crystal. There are 23 elements of there in a cubic crystal. Right. So, in this video we have discussed in detail about the crystal structure, elements of symmetry in a crystal, different types of elementary, and we have calculated the total number of symmetry elements in a cubic crystal, and we have counted, and satisfactorily we have understood the concept of crystals in this branch of chemistry. We shall continue in the next video regarding the axis of symmetry. Thank you.